Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. There are strong lights today. My name is Francesco Petruccione, and I'm the director of NITheCS. And this afternoon, I'm very pleased to be able to introduce you Professor Nico Orce. Nico is, sorry, I think my laptop, yeah. Nico is based at University of the Western Cape. He's a nuclear physicist, but has also interests from mathematics to biology, and has published also so widely. Yeah? Nico conducts experiments all over the place. Yeah, from Itemba lab close by to CERN and SALT. Yeah, from the small to the big, and probably everything in between. Yeah, and today he will update us on his recent research on what nuclear thermometers can do to show us the abundance of heavy elements in the universe. Yeah, Nico. So thank you very much for coming the long way from the University of Western Cape. We are
Thank you
very
so much.
much looking forward to your talk. Thank you.
Thank you, Francesco. Thank you. Thank you, Francesco and NITheCS for the invitation. So today I'm going to update you on what we have pursued, the science that we have done in the last few years. And this is a drawing I made myself for this particular occasion, where you have the kilonova ejecta. You have obviously two neutron stars merging. You have the jet produced by the confined magnetic field. And maybe this is a picture of gravitational waves. But what I'm interested in is in these elements, these ionized strontium and double ionized tellurium, which have been observed in that kilonova ejecta of neutron star mergers. And this is the evidence for the astrophysical side where elements are created in our universe, heavy elements beyond iron. So we have a big problem in nuclear physics and quantum mechanics because we are dealing with a lot of possibilities. This is the binomial theorem. And as you have more than 20 particles, this goes to 10 to the 11, 10 to more than 10 to the 11, 10 to the 12, 10 to the 20, 10 to the 70. You know, we have an infinite many-body problem given by the Hilbert basis space, and we're going to solve the Schrödinger equation in many other occasions. We have untractable mathematics, and also ignorance of the potential, because Hamiltonian is equal kinetic energy plus potential energy. So we don't know exactly what is the potential energy of the nuclear force. This is the nuclear-nuclear interaction. And as Marun and Greiner mentioned, we are dealing with a system of particles whose number is neither small enough to allow direct solution through the Schrödinger equation, nor large enough to make statistical methods highly accurate, and which interact through an interaction that has not yet been pinned down to any definite form. Right? So we have this is, I would say, the mother of all problems. Mathematically, physics-wise, whatever you want to call it, this is the mother of all problems, the many-body problem. And what another indication of how this is an issue, this is like millions of cores. This is the largest supercomputer at Oak Ridge National Laboratory. It's called Frontier. And these guys can only calculate a little tip here of the nuclear shard. This is the whole nuclear shard. This is number of neutrons and number of protons. I can reach maybe oxygen 16, 20 neon at the best. So not with 200,000, with millions of cores. We can go any farther without playing games, without doing truncations or integrating out the model space. So this is not the way to go. I know I'm not in the right place to say with Francesco here in front, but even quantum supercomputers won't help us. So we need to identify, those microscopic properties which can be measured in experiments and trying to infer what is the nucleus in this particular case doing. Regarding this point, we just got this paper accepted about how collectivity of the proton and neutrons arises from knowing what is the atomic masses, right? So from the atomic masses, which I call them macroscopic properties, because atomic masses, imagine you have a football stadium, the atom is the football stadium, and the nucleus is the little head of the needle at the center of the pitch, right? So we are talking in terms of macroscopic, for me, atoms, where we can actually measure those masses very, very precisely. And from those masses, we can deduce what is the nucleus is doing, what are the transition probabilities, what is the collectivity of proton and neutrons interacting with each other. There's a new paper which has been accepted, as I say, and will be published soon. So, but today I want to try to do the same and try to extract some information about the following problem. You know, why do we observe the same amounts of gold, silver, platinum throughout our universe? It's a question that hasn't been answered so far. And, you know, it was in a review article in the Progress in Particle and Nuclear Physics, the current status of this is the rapid neutron capture process and how elements are produced by capturing neutrons. And these observations in different stars, metal poor stars and galaxies, suggest a rather well-defined origin of heavy elements beyond iron. We do not know if this may be only an artifact of nuclear properties such as binding energies or bit decay rates, or it may point to a single cosmic site with astrophysical conditions that are generated uniformly throughout cosmic time. You know, this is the situation is that we don't know, or we didn't know. So here, also a fundamental question that we're going to try to answer: how were those elements from iron to uranium made? So this was a Discover journal where this was one of the 11 unanswered questions. Atoms heavier than iron are minted, where there is a ready supply of neutrons, although the specifics of how this happens are known. More recently, some of the heaviest elements, such as gold and lead, are formed in powerful blasts that occur when two neutron stars collide. So these are the experts telling us that we don't know what is happening here, why we see the same amounts of heavy elements, and how they are created in the universe. So, however, we can always, you know, if you don't need to ask the expert, we can go to ChatGPT and ask the question. It will always provide an answer which, you know, in summary, you know, you're asking the question, how were the elements from iron to uranium made? In summary, elements from iron to uranium are created primarily through stellar processes, explosive events, and cosmic interactions, illustrating the dynamic and interconnected nature of the universe. This is like saying nothing, you know, because there are no specifics, there's no details on the explanation, right? These are politicians talking. If we believe these things, in 10 years' time, we'll be speaking like these guys, talking nonsense, talking empty sentences. So you have to be very careful with ChatGPT and all these new possibilities because they enhance the weak, but I think they corrupt the good science. So this story happens starting in Oxford. I went there to give a talk when I was a student. And it was in a conference where I was asked the question about the binding energy formula, the semi-empirical mass formula. They asked me, it was an international conference, the winner will go to Hungary. And they asked me this question. I said, well, I don't really know this thing. I thought this was obsolete or just, I don't really know if anyone is using it. So with the result that I didn't go to the international conference. Although, you know, I won the popular vote, but that wasn't enough. So I don't think so. You know, these kind of answers don't help you. So what I didn't know at that time, and it's very nice to see that actually this whole work started in Oxford and also finished in Oxford, as I will mention in a little bit, because it was published in Oxford University Press. And at that time, I didn't know that the convergence of this symmetry energy for heavy nuclei establishes this frontier of nuclear existence, which is the neutron tripline, right? I put a picture of Roger Penrose because I love him when I've seen him giving talks, and he represents Oxford in a way. So this terra incognita here, this is the neutron tripline, and everything happens according to Einstein's formula. This is the binding energy, which obviously is the difference of the masses times c squared. And this binding energy, as you can see, is here represented by different terms. And any negative makes the nucleus more unbound. As I mentioned before, the convergence of this number, this constant here, determines these limits of existence, of nuclear existence. After this, the nucleus becomes unbound, and we have no more nuclei, right? So this is the whole thing here. How far can we go? Where is this terra incognita? Where are the borders of existence? And that's it's a number I will show you now what it means. So it's a number, yeah, but it depends on the mass also. But I will just mention it in a sec. So first, about the balance of elements above iron. What we know is that we have the S process, which produces about 50% of the elements. And we know very precisely, we assume that we know very precisely the S process. And we have the Gaia satellite here, which give us some more information about these unstable atmospheres, how these elements are ejected into the outer space and adding to the abundance of elements. And the rest of the other 50% are created by the rapid neutron capture process. The S is the slow neutron capture process and happens in the interior of AGB stars. And the R process happens in big stellar explosions with lots of neutrons, right? So as we don't really know what is the R process, we assume that whatever is missing from the solar abundances, if we know exactly what is the S process, the remaining should be the R process. That's how we know this red curve. So this is a typical picture of the S process, goes along the line of stability, along these black squares, which are stable nuclei, and you capture one neutron. We don't have so many neutrons to go farther. So as soon as you capture one neutron, you beta decay. Always you go back to the line of stability, right? So this is the S process happening in the interior of AGB stars. And here we have the predictions of the triplines for the R process path of this network of nucleosynthesis calculations that limits the nuclear existence. As you can see here, there's a bunch of different possibilities with, depending on the different mass model, right? So predictions for neutron tripline and their process path involving heavy neutron-rich nuclei exhibit, as you can see, a significant variation due to the wide range of conditions, experimental conditions, which are unknown. In particular, atomic masses. Farther from stability, in this terra incognita, we don't have, this is what the F-rib limit is here. This is what we expect to measure, but nothing else beyond is possible at this moment. And that actually limits our understanding of our process network calculations. So studies of nuclear interactions in systems with high or extreme neutron to proton ratios are crucial for understanding the neutron tripline, which again comes back to the convergence of the symmetry energy for heavy nuclei. I will answer questions right now in a little bit. So these are sensitivity studies done for their process network calculations. And you can see this is the maximum difference between theoretical nuclear mass model predictions over the chart of nucleides. And you can see here there's 2 MeV. This terra incognita is very much unknown. What are the masses there? And the masses is a key ingredient, as you can see from Einstein formula, because the binding energy depends on those masses, right? So if the nucleus is not bound enough, you won't go too far into the terra incognita, but you go directly to the line of stability. And here you can see a plot where you have different mass models which differ by 300 keV in RMS. In the RMS, so this 300 keV doesn't allow you to distinguish between an R process or a supernova, for instance, right? So this line, actually the yellow line, represents the maximum and minimum abundances for in these studies for each abundance. So here we see the discrepancy, the difference between different mass models. As you can see, as you can go heavier in neutrons over 120, you can see that the different mass models really diverge quite a lot. So we don't really know what is happening into the terra incognita, and we don't really know the limits of existence for nuclei. And as you can see here, at least we need 100 keV RMS error in these mass models to actually be able to distinguish between different astrophysical scenarios. So here we have a different approach, which is based on the Bayesian statistics. And in this way, we try to infer. If we don't know the masses, let's say if we know this mass, what happened? Then we can we identify, if we know these masses exist, obviously the unknown mass can be determined. But this depends obviously on the information that you have. And sometimes it may happen that you don't have enough information, or the information is drastically different to what you know. So then the Bayesian method won't work. So predictions made with 11 global mass models and Bayesian model averaging. Again, you have a huge difference because basically there's a missing ingredient here, which they're missing. So if the nuclear physics will be known, then there wouldn't be so much of variation here. But however, you can see that sometimes statistical methods, they're not as relevant as we may think. So although they are very interesting, obviously you have a likelihood of something to happen, you have a prior knowledge of something, evidence, and you try to calculate the posterior. Easy to calculate this Bayes theorem using the conditional probability here. This statistics obviously is based on the context. As you can see, the problem of the three prisoners, which is very well known in Bayesian statistics. But it's very important to know something, the context. But if you don't know anything, or you are missing something very important, then this method won't work. So these are some of the work that we are doing right now. Tony Linus Gray from UCL is here with us, not here in particular, but he's working at UWC when giving this talk. And we are using the Markov chain Monte Carlo, another statistical method, the stochastic in this case, to investigate metal poor stars. And this is just an example of having barium and strontium ionized lines here. And you can see from a metal poor star in the southern hemisphere that we have identified, or we observe with salt, we have 6 nights. And you can see the different ratios tells you whether you have these elements produced in these metal poor stars came from the slow neutron capture process or from the rapid neutron capture process, right? So these things tells you how the first stars, how the elements in the first, on the oldest stars were produced. So here is the evidence of neutron-star mergers, as I mentioned at the beginning, this blue shift. Then here is strontium, supposed to be strontium-2, and there's also some yttrium as well. But I just mentioned here, be careful because the opacity of these stellar environments matters, and if the opacity change, you could have the same phenomenon having helium-1, and then you are missing the whole production of heavy elements, right? I just tell you this, although people are concluding that this is the most likely possibility to have a strontium, ionized strontium lines in the afterglow of the kilonova as it cools down. So there's more evidence here, another tellurium-2 line, emission line here, also was identified recently and published in Nature, as well as the other one. So here is the evidence for universality of abundances from baryon to lead. And as you can see, it agrees very nicely with the solar arc process, which is the blue curve. You have different stars, and the abundance patterns of the heavy elements from baryon through lead in the most metal-poor stars are consistent with the scale solar system. Our process only abundance pattern. So which tells you that there's a general pattern, there's a universality of elemental abundances. So here there are more examples. On the Reticula 2 is a galaxy with mostly our process stars. And you can see that given that the sun actually formed billions of years after these metal poor stars, which are the oldest in the universe. So by many stellar generations in various ways, the elements that we have in our sun, they're not produced by the sun. The astounding agreement between the patterns suggests that the arc process is universal, right? So these are the things that we have seen through observations, but cannot be explained. So now I want to bring it down to the nuclear physics, how we can measure those nuclear thermometers, how we can measure the ejecta, the kilonova ejecta from the neutron-star mergers. As you can see, there's a comparison here of binary neutron-star mergers with heavy ion collisions. And we see that the kilonova stars with a temperature of 40 to 50 MeV, which is like 5 × 10⁻11 Kelvin for the astronomers. We normally work on MeVs. And then as it cools down, you start producing, bursts, the hadrons, quark, gluon, plasma, proton plus neutrons. And then eventually you reach the temperatures where seed elements are created before charge reactions freeze out. And there's a high neutron to seed ratio. And after that, just below that, around 0.4 and 0.5 MeV, less and equal than that, the neutron capture starts occurring in the arc process. And this is how the elements, about 50% of the elements in our universe, are supposed to be created. And then neutrons are finally consumed, and you go back to the T = 0 ground state. These are the temperatures that we're talking about, around 0.5, 0.71 MeV, and T = 0, you don't produce anything else. So now we are going to identify that nuclear thermometer. And the nuclear thermometer must be something which has similar properties. And this is what we propose in this particular case. They are called the giant dipole resonances. And the giant dipole resonances are the first, actually, collective motion of protons and neutrons oscillating against each other out of phase, which creates a large production of gamma rays, torsion and emission of gamma rays. And, this is the highest electromagnetic radiation produced by nuclei is coming from this motion, which can also be reproduced macroscopically by proton hole excitations in shell model calculations. So this is the way we're going to investigate how the cooling down of the kilonova happens at different temperatures. And we're going to be using the property of the Brink axial hypothesis, which stated by Brink in Oxford, that a GDR, a giant dipole resonance, is built on every excited state, right? So in that sense, we can have here the ground state GDR built on the ground state, and you can see the dashed line corresponds to ground state GDRs, and these are the circles, and the solid line corresponds to GDRs built on excited states, right? And you can see that very similar features, very similar properties, not only for the energy of the giant dipole resonance, but also for the width of the resonance. So this work was originally thought of to check the influence of shell effects at high excitation energies. And these findings open a new avenue of investigating magic numbers and high excitation energies, which we did in the work I'm presenting now. But it was a beautiful work to do to see that for the first time, these photoabsorption cross-sections of this giant dipole resonance provided information on how the nucleus behaves, or what is the nuclear structure, and what are the subshells and shell gaps in the nucleus at high excitation energies. So this, you can see here how as you reach one of those semi-magic numbers, these are magic numbers for neutrons, you can see that there's a sudden drop of these elements, here again. So N50, which is this line here, N28, N82, and N126. And this sigma minus 2 is basically the total photoabsorption cross-section divided by the energy of the gamma ray square and integrated between 0 and infinity. But obviously, there's no 0, there's no infinity. That those limits depend on the experimental, what is available experimentally. So we kept investigating the sigma minus 2, is related to the dipole polarizability, and we could see that there was a missing gamma p, which is very important here because the Coulomb barrier is not so high. So the gamma p competes with the gamma n contribution. These are all these data points at gamma n. So at that time, this is very important for the equation of a state, to try to get this surface, the volume and the surface term of the symmetry energy right. So this is the first indication, as Jinsei just mentioned, that symmetry energy change with mass, and you can see there's a change of variation with mass number. So it's not just a constant; depends on the number of proton and neutron. So furthermore, we deduced a formula which was based on the evaporation model of Blatt and Weisskopf, where you have a ground state T equals 0, and you go and this is not temperature, in this case also temperature, but in this case isospin, and T equals 1 is isospin. There's a change of isospin always in this giant dipole resonance, and then you have the competition of the nucleus to go gamma p by emitting a proton, or gamma n by emitting a neutron. So this ratio gamma p and gamma n for heavy nuclei is dominated by the gamma n, but for light nuclei, in particular for this nuclei with the same number of neutrons and protons, we see that there's a nice curve here, which was explained in this paper here. So that's the ratio of gamma p on gamma n, which actually dominates, gamma p dominates gamma n, and can explain the drops that we saw right here. So all these have to be under control when we do this kind of work, because we need all the photoabsorption cross-section, because it comes into this equation here. As I mentioned before, the sigma total is the total photoabsorption cross-section, and this depends on the inverse energy weighted sum rule, where we have all these matrix elements, dipole operators connecting the ground state to the giant dipole resonance, to that collective behavior of protons and neutrons, and going down to the ground state. In this case, this will be the dipole polarizability of the ground state. And we can use the hydrodynamic model as done by Migdal and compare the two of them to extract this simple formula, which was proven experimentally by Levinger in 1957. And we did a new, it was 3.5 according to Levinger. And we got the data, the most recent data, and we just got closer to that, where this kappa is telling you the difference between the real giant dipole resonance effect, the real microscopic. These are like, can be thousands and thousands and thousands of these transitions up and down, compared to the more microscopic model. So this kappa is the difference between the real giant dipole resonance effect compared to the hydrodynamic model. So, and this is the symmetry energy, again, with a mass dependence. It depends on the sigma minus 2 value and a to the 5/3. So, furthermore, we know that the symmetry energy can be characterized by the giant dipole resonance, the energy, and the width of the energy. The fact that we have the Brink axis hypothesis allows us to say, okay, this was done normally for the ground state GDR, But let's see what happened with other GDRs built on these states and see how. Needless to say, I have to say that the temperature goes from 0 going up. You know, the higher you up here, the higher is the temperature. So that's where the neutron star, we're trying to reach where the mergers, the neutron star mergers are happening, right? So these similar features indicate a common physical origin of all GDRs and allow us to understand these GDR as spectroscopic probes as a function of temperature or thermometers, nuclear thermometers. So this parameterization has been done in many occasions and works very nicely, as you can see here for the giant dipole resonance in lead 208. There's some high order effects, but these guys are not so important to us because sigma minus 2, or the polarizability, is inversely proportional to the E gamma square, as you can see here, right? It's more important what is happening in the low energy regime of the giant dipole resonance. And so this was the data that we have for the ground states. As you can see, there's a saturation around 27 MeV. And this saturation, if you just take the binding energy curve, you will see that. I will show you a plot now, how the binding energy reduces, how the nuclear short shrinks towards the line of stability, depending whether this value is large or small. So if we assume that we have the same properties for GDRs built on excited states, this is what happens. As you can see, these are for ground states, and these are the GDRs for built on excited states, right? It was in the range of 0.7 to 1 MeV. As you can remember, 0.7 MeV was the range where we produce these seed nuclei, and then they get captured neutrons, and they create the elements that we see around us. So this was explained, assuming that we have an effective nuclear mass which breaks the non-locality of the Hamiltonian and is needed to characterize the levels around the Fermi surface. This was published by Donati and collaborators in 1994, and they calculated that this increase gives a symmetry energy increase of 8% at about 1 MeV, which is what we see in this plot. So furthermore, we just identify a nucleus, this guy in particular here, chromium 52, which follows the line that we see for temperatures. Now we go down to 0.5. This is the only data which is below 0.7. And as you can see here, there's a 0.5 data point for chromium 52. As you can see, the temperature dependence of the symmetry energy doesn't change much in this temperature range, which is quite surprising because we were hoping to have a phase transition somewhere here, but it seems like the temperature behaves quite smoothly. As I can show you here before, at temperature 0.5 or around 0.5 MeV, the neutron capture starts occurring. So this provides evidence that actually we have a large symmetry energy at our process. So we change how the nucleus gets bound, right? This has strong implications, as we're going to see right now. So this is one of the first implications as symmetry energy. And now answering Jinse mass question here. We have 23 MeV. We can fit nicely the atomic mass evaluation, the 2020, at temperature equal to 0 MeV. Most of the data that we have, obviously, is in the graph for the ground states. We don't really know what's happening up there in excitation energy because we cannot measure those masses. However, our giant dipole resonance tells us that there's no such thing as, it's more like 30 MeV, and there's just a relative binding will be this blue curve, which actually tells us that the nucleus become less bound, and obviously the drip line will shift towards the line of stability. So as you can see here, this is a plot where you can see the typical 23.7 MeV in the astronomy books and you can see what happened up there at the excitation energies relevant to the process nucleosynthesis. As you can see, there's a huge shift of the limits of existence for nuclei, and here, I don't know, this was confused, but imagine there's a red line here, and there's around the terra incognita, but then suddenly you have a green line, which is not, basically, the terra incognita is not that big. You know, it's not like huge. We don't go so far off the line of stability, but we are much closer to the line of stability, which obviously there's a reduction of the neutron capture cross sections by a factor of 100 in the mass 200 region. This implies that we're going to capture so many neutrons, but quickly we got to go back to the line of stability. And this capture of this beta decay to the line of stability adds to the abundance pattern, or how many elements, how much of gold and silver depends on that. So now you can see a little plot here where you can see the broad nuclear shard with 23.7 MeV and how it narrows down at 30 MeV. So there's a closing, or a shift of the neutron drip line towards the line of stability. And again, I mentioned this, the convergence of the symmetry energy for heavy nuclei established as such a frontier. It was published last year, not with the new results. It was published between 0.7 and 1 MeV. That was the temperature where we got these giant dipole resonances and where seed nuclei are produced before they start capturing neutrons, right? This was a very nice publication, I think, where we set up the foundations of why do we see the same amounts of gold in our universe. Again, we can ask ChatGPT. I will tell us that while gold is distributed unevenly throughout the universe, the overall amount stays relatively constant because it's not significantly altered in quantity by the processes occurring in a star or galaxies. Again, a lot of blah, 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 politician talking. We want to know the specifics of how things happen, and that's what I'm explaining here. So, still need an additional explanation of what is happening. We have Donati's effective masses, but still we don't know when this is happening, when is this phase transition, suddenly why the symmetry energy changes, right? But still we need to develop further this story. So as I say, supercomputers cannot help. However, they are always useful, solving the Schrodinger equation for these masses, or for these heavy nuclei. But we can always make truncations or integrate out the model space in a way that we can have an inner core. For instance, this is a typical case of having oxygen-16 with 8 protons and 8 neutrons. Both of them are magic numbers, so they're very stable, like in atoms. We have the noble gases, very stable, right? So we assume that this is very stable and doesn't contribute to the excitation of, say, something with 10 protons and 10 neutrons, say neon 20. So we'll have 2 protons here and 2 neutrons in a similar shell with the same labeling here. This is the N quantum number, this is the L quantum number, and this is the J, which is L plus minus S. S is the spin, 1/2. There's a jump between these of 41A to the 1 minus 1/3, according to the harmonic oscillator. It's not 100%, but it tells you, it gives you an idea, because the good thing of the harmonic oscillator is that the wave function can be calculated very easily, even by anyone can do that, following the RDN, the Hermite polynomials. And we do calculations of thousands of matrix elements connecting here to here, right? So these E1 matrix elements, which I mentioned before, we actually calculated them, and you produce thousands of transitions. You can see here for these nuclei, for neon 20, for magnesium 24, and argon 36. We have thousands of states which determine the B1 of the transition probability, but also for these you need to get, again, all the transitions going up basically this represents the giant level resonance is proportional to the B1 probability. And you can see here the formula. But in this case, the initial and the final are the same, and the final and the initial is the same thing, right, for the ground states. And this is key here, because the polarizability for these nuclei, as you can see, is around 2 for most of them, calculated. There's very little experimental work here, lots of theoretical calculations, including ab initio. That was for the ground state. For nuclear excitations, we had to develop a new theory. We had to develop new equations that were also published here. And this paper was among the top most read papers for a month or two, where we deduce new equations to deduce what is the polarizability of these excited states and how do they compare with the ground state that we know very well. As you can see here, as you go up there, the dipole polarizability characterized by this parameter kappa, which I mentioned before. This sigma minus 2 is proportional to alpha, and this kappa is basically telling us the effect of the giant dipole resonance as compared with the hydrodynamic model. And as you can see here, there's a drop of the nuclear polarizability. The reason behind this drop at first excitation may be related to the rise of alpha clusters, which adds additional binding to the nuclear system. And this is the fact of the matter is that it depends on all the E1s up and E1s down. Here, you don't have the square anymore, and this guy can be negative and add destructively to your total nuclear polarizability. So this is the case shown here. Actually, this is just the same thing, but just shown in the same slides where we are calculating this, and we are calculating this here, right? All the E1s going up, and then to the final state, which is an excited state, and in here we go to the end state, which are the giant dipole resonances, also here, but the initial is the ground state, right? The ground state to the final state. That's the picture we have for the thermometers for this oscillation I showed before. So what happened here is, and this is the new paper submitted to the monthly notices. What happens is that the 0 plus ground state to the giant dipole resonance state, which are characterized by 1 minus, and the 1 minus to the first 2 plus, it start having some negative contributions here, and this actually reduces the nuclear polarizability of the first excitation with respect to the ground state. It was actually what Donati mentioned in 1993 in his physical review letters, that this effective mass will be the main player for this change in the effective mass of the nucleon. Will be these first 2 plus. In this case, the first 2 plus or the 3 minus. Also, there were 2 states, depends on the nucleus. But for these cases, we don't have a 3 minus, it's 2 plus, which is the main contributor to this change in the nuclear polarizability, which happens not very high in temperature, but happens down close to T equals 0, close to the ground state. And it is simply because of the negative contributions of the product of the matrix elements. It doesn't happen here, right? So this is the macroscopic explanation of why we see the same amounts of gold, silver, and platinum through our universe. This was proposed before. Similar picture where they calculated a symmetry energy, a large symmetry energy here. This large value for this ratio favors a closing neutron drip line for heavy elements, and hence argues against the production of super heavy elements by the Orce process in supernova. That was a little bit too harsh. This one is a little bit better, I think, because the calculations here, there's a drop for those neutron-rich nuclei as you get closer to the neutron drip line. The universality of the Orce process abundances could possibly be explained by the rapid drop of the macroscopic, actually, neutron capture rates here. This is the macroscopic versus the macroscopic, at increasing neutron excesses, which constrains their process flow to remain in the narrow region of the nuclear chart characterized by low beta half-lives, and large neutron capture rates. Basically, we are saying that this terra incognita doesn't go too far off, but it stays much narrower than predictions. Basically, it's telling this. So if we are flying, we are driving to Pretoria, you take the N1, but the N1 is, you get too far away, you're going to get lost somewhere in the jungle. So basically, this line of stability, you cannot go too far off and create this terra incognita because the nucleus becomes unbound. You're going to go too far into that terra incognita. The same thing here. You go too far here, you get lost, and it's not good to get lost these places if you don't know them. So that is what I wanted to tell you. That is how we have concluded that. Obviously, there's more experiments that we can do, but we use these giant dipole resonances as thermometers to determine a large asymmetry energy, now in T equal 0.5 to 1 MeV, and results in a shift of the neutron drip line towards the line of stability, which constrains the process flow and narrows down the nucleosynthesis path and provides an interpretation to the universal pattern of our process abundances. Caution, the present work assumes the validity of the empirical mass formula, but we try other mass models, obviously the same thing. If we have the Bring axle hypothesis, where we assume that the giant dipole resonance is built on every state of the nucleus, and we have to just to characterize what happens at temperatures below 0.5 MeV. And for that, we have the CAMCA array, which is the largest grant ever given by the National Research Foundation, 35 million rands, which was commissioned in 2021 and is at the Temba Labs, hoping to be used as soon as possible. So these are other experiments that we are doing at the high solid at CERN, and we have other experiments approved, but we need the CAMCA we need beams actually at the Temba Labs. We don't have beams at the Temba Labs for many years, and this is the pity, because we have like having a Ferrari out there, but we cannot drive it. So we are waiting for the Ferrari to drive and get lots of kilometers. So we also have what happens far from stability. We don't know. As you can see, the mass models, they vary a lot. And then I also mentioned briefly what happens with SALT and the HRS and infrared spectrograph, a new one called NARVAL, where you can actually explore through observations these metal poor stars and this universality of the elements. So I think I will conclude with a little bit of the previous ChatGPT, I would say, but a little bit more consistent ChatGPT. This is a very famous scientist. The composition of matter, as we see today, is the product of nuclear reactions which have been taking place a long time ago in the stars or in star explosions. Hence, the material basis of the world in which we live is a product of the laws of nuclear physics. Again, it's good to know these things, but the specifics have been explained today. I cannot better illustrate the interconnection of all facts of nature, the tightly woven net of the laws of physics, than by pointing to the chart of abundances of elements in our part of the universe. Each maximum and minimum in the curve of abundances corresponds to some trait of nuclear dynamics. Here a closed shell, there a strong neutron cross-section or a low binding energy. Beautifully said. Specifics I presented today. Thank you very much.
Thank you very much, Nico. Thank you very much for the very nice talk. Are there questions for Nico? Please. Microphone is coming from the top.
Hi, Nico. Yes. There was a slide which you show the sigma -2 and also the value of asymmetric, A sub sim. There, possibly reverse further back.
Back, okay, sorry. Let me use this thing. I think this thing is this one?
Further back.
Oh, further back. Okay, sorry.
Yeah.
Yeah.
Yeah, this one. Yeah. So here I don't understand. I mean, let's say you got your sigma -2 calculated in that equation, the second line up, second the below one, that your sigma -2 is proportional to a to the power of 5 divided by 3, so
Right.
5/3. And then that will, if you substitute that back to that equation, you will cancel that a to the power 5/3. Then you just get a constant of
These two, you are calculating this formula from these two, right? So you have this factor here, which is sigma -2, right? And this is related to alpha, so you just equal the two alphas and get this sigma -2. So you are equaling this equation, the hydrodynamic model, and the perturbation theory, right? So
yeah, but then if you substitute that result into the last equation in the box, then you cancel that a to the power 5/3 dependence, right?
yeah,
And then you get a constant of a sub sim. Is that correct? Or
for sigma -2, you see, if we just do the calculation here, sigma -2 is equal to alpha, right? So sigma -2 will be 2 pi squared over h bar over c. That will be, or alpha will be equal to this. Alpha equal, if you just equal these two terms, you can get this formula if you assume a symmetry energy, a constant symmetry energy in this case.
okay.
That's what Migdal calculated. Use the typical thing was 22, 23 MeV symmetry energy, which he used as a constant value to get this 2.25, right?
So you already assume a sim to be a constant.
He used a symmetry to,
Okay.
Migdal, not me.
Okay. And the other question is, look like your convergence of that A sim A is dependent on the temperature, as you have
Right.
shown later on in another slides. I mean, not these slides anymore, but future slides. I think later slides.
Yeah.
I think there was a slide showing, yeah, like
This one here, right? This one.
yeah. Then maybe the next one, maybe.
Right. So these are average temperatures, right? When you produce this, you are basically producing, it's a fusion evaporation reaction. So you cannot really determine precisely what is the temperature. It's an average temperature, which depends on the level, density of the states, depends on the spin or the angular momentum of the state that you're populating. So say, for instance, if you have a very heavy ion reaction of lead-208 on lead-208, so the nucleus will rotate a lot and produce lots of very high temperature, right? The more heavy ion reaction collisions that we show at the beginning, actually, in this plot where they deduce that we have 40 to 50 MeV for the kilonova ejecta, it comes from heavy ion collisions, right? So that you can go to 40 MeV because the nucleus is getting very high excitation, right? By having two heavy nuclei colliding. But you can go down by having, say, for instance, alpha prime. If you interact light nuclei and you do scattering, you can actually reach these lower temperatures that they're interested in astrophysics, right? This one, there's a lot of information above here, but we don't care about those because those are the cooling down of the kilonova where elements are not produced, right? So is this starting here with the seed nuclei matters and starting here where the neutron capture matters, right? So these things are determined by, let me see, by this plot I showed here before. So you have a different coincidence of high energy gamma rays, and all these are in coincidence. So this big gamma ray, depending on the fold distribution number of multiplicity of detectors being fired, it's quite a technique in trying to get an average temperature, an average angular momentum. But that depends roughly on your reaction of interest, right? So the best thing to get to these temperatures is to have light nuclei interacting with each other, right? Light heavy ion collisions or light scattering reactions, right? So that's the way you reach to lower temperatures. Did I answer your question?
I think my question is that possible that A sim is also dependent on temperature?
Right. A sim depends on temperature. That's why we are saying here that depends on the temperature, AC, you see this is for temperature equal to 0, the red plot, right? This is for ground state temperatures. And this is for temperatures between here and here, right? So it depends on temperature, as you can see, but within this interval, it doesn't change much, right? So where does it change is what I explained. It changed rapidly for the first excitation of the nucleus because of these contributions, positive and negative, right? So the symmetry energy depends on the temperature.
Yeah, one more question, please.
Thanks for the talk, for the presentation. So when you calculate your polarizability from the nuclear model, how sensitive is it to the details of that model? For example, in nuclear potential, and or is it?
So we have that's a very good question as well. So here we go. Right. So this, for instance, is the ground state polarizability, right? So obviously it depends on an interaction, and that interaction is very important. But we have seen from our initial calculations that this dipole operator converges. You know, as I mentioned at the beginning, the trick of the Hilbert space that you must converge with the interaction must eventually converge. The whatever you're calculating must converge at infinite.
You mean the sum over n converges? Or what do you
Yeah, this converges, you know, at m max of whatever, you know, in the harmonic oscillator. So these thousands of states, they are kind of well characterized, unlike the E2 operator, which is a more collective operator, and ab initio calculations don't converge. So there we are more confident that this, from ab initio calculations from first principles, that these E1 operators are, you know, we have them almost under control. I would say almost under control because you see, we are calculating lots of thousands of them, right? And the interaction that we use, I didn't go into the details, but the interaction is the PSDFP valence space, right? So basically it considers the alpha particle as an inner core. So the rest of the particles are moving around in a way, but this interaction is determined empirically. So it's like a mixture. You know, you have all these energies, all these masses, and you put them in the mixture and fit the two body matrix elements. So the issue here of the beginning, the formula I showed at the beginning, is the two body matrix elements, how these interact with this guy, with that guy. And those 63 or whatever matrix elements are in the SD shell or in any of these shells depends, in this case, of the empirical fit to the interaction. So this is the issue with nuclear physics in particular, because we don't know a potential, right? A real, what is the final?
Was my question. So how sensitive is it? So there are several potentials on the market: a Bond potential, Paris potential.
Right.
So if you use different potentials, do you get the same results or?
So you see, these are the first time these calculations have been done, right? And there was these calculations for these nuclei the first time. Our initial calculations cannot reach there. So this potential normally are used nowadays is more the chiral effective force, you know, this potential from chiral effective field theory, which comes on the same footing, the two nucleon forces with the three nucleon forces with four nucleon forces on the expansion diagram of the Lagrangian, right? So these are the potential that they are used nowadays, but they cannot calculate these things, you know, so far. So maybe we're encouraging them to calculate those with. What I rely is we have done the comparison for carbon-12, where we have our initial calculations and our model, our empirical interaction. And there we see a convergence of the two, right? So we are comparing our calculations with calculations from first principle where principles can reach, right? For instance, carbon-12 is the perfect benchmarking nucleus because all these theoretical models can reach there. The 10 to the 10 dimensions, right? Above carbon-12, the situation becomes more serious, and we cannot compare with first principle calculations.
Thank you.
Questions from the online participant? No question. Please, one more question here, please.
One question. Could you please explain me what is R in this expression of alpha?
This is the radius. This is the R naught 1.2 a to the 1/3.
So this is depends on the 8 to the power of 1/3.
That's
That is why you will reproduce this 8 to the power 5/3 result.
right. That's right. That's why you got this. So
Okay.
this is
R is depends on A. That is why you will get the correct power law. Okay.
right. That's why you get the 5/3 because R is
R is depends on
1.2 a to the 1/3, 2/3, 3/3, 5/3.
And then last ask the Roger.
More questions. It's good.
Can I lastly ask a Roger Penrose question again? Do you still use that formula of binding energy?
I use it because, as I say, we close the loop. Independently of the model that you use, there are more sophisticated mass models, right? But there will always be a difference in the symmetry energy for the ground state as compared to the excitation, right? This is just a way of illustrating in a simple way that the symmetry energy changes, that the properties that we know at those temperatures where stellar explosions happen, we don't really know them, right? From experiment. From experiment, we always measure the ground state. So in that sense, I like to show that plot, that slide there because it's like telling us, for me, these little things are important, because you go to an international conference, right? And you don't win because you didn't answer the question right. So there's going to be eating me forever, until I publish in Oxford University Press, I'm happy. But I'm not happy enough, so I'm going to publish another one in Oxford University Press.
Okay, if there are no more questions, then let's thank our speaker very, very much. Nico, thank you very much. And I would like to give you a copy of this famous magazine that NITheCS publishes. So thank you very much, Nico.
Appreciate it.
Thank you very much for your talk. And thank you also to the